Hi everyone, my name is Luca, and my talk today will be about correlation detection in trees for partial graph alignment. This is a recent joint work with Laurent Massoulié and Marc Lelarge at INRIA in Paris. So first of all, let me introduce the graph alignment problem. The graph alignment problem originally is a combinatorial optimization problem. So assume that we have two graphs, G and H, and we're asking the following formal question. What is the best way, in some sense, to match the nodes of two graphs? Well, this question is quite general, and one possible answer can be brought by designing some objective to satisfy, right? So in the case where the two graphs have the same number of nodes for simplicity, we can ask the problem as follows. We want to find a bijection from the nodes of G to the nodes of H that minimizes the following quantity here. So this quantity is the number of edge disagreements between the two graphs. Namely, we want F to preserve most of the edges, right? So if I and J are connected in G, then F of I and F of J are also likely to be connected in H. So in the case where the two graphs are isomorphic, you can easily see that this problem is simply the graph isomorphism problem, of course. But here we're asking the problem in a more general setting where G and H may not be isomorphic. Right, so this problem can also be rephrased as follows. We want to maximize the following quantity here over all permutation matrices of size n times n. And this is an instance of a famous problem in computer science literature, which is the quadratic assignment problem. And this problem is known to be NP-hard in the worst case. Okay, so to go beyond this difficulty, what people do in general in the CS literature or in the probability literature is that they consider another related version of this problem, which is the planted version of graph alignment here. So what is the planted version of this problem? So the idea here is to study the problem in the mean case setting, so not in the worst case setting anymore. And doing that, we are actually looking at graphs that are drawn under some random model. And we are looking for guarantees with high probability. So now the objective is a bit different because we plant a solution in the data. So the two graphs will be generated according to some planted solution pi star, which will be in some sense, the optimal assignment. And we just hide this planted solution. We observe the two graphs, and what we want is an estimator of this pi star, right? So we want to recover, in some sense, pi star with high probability. Okay, so now let me describe first the random model we are working with. If you're familiar with random graphs, you won't be surprised here that we use the correlated Erdős-Rényi model. So this model is very simple, except that here we have two graphs, so we have to think about correlations. So we simply draw every edge independently. So imagine that the edges of J are blue and the edges of G prime are red, for instance, with the same node set, then every edge I and J will be either two-colored with probability lambda S over n. So this means that the edge will appear in both graphs, or it will be monochromatic, so blue only or red only with probability lambda over S, or lambda 1 times S, sorry, lambda times 1 minus S over n. And with the remaining probability, this edge will simply not exist. Okay, so this is the first step. We generate two correlated graphs, and then, as I said, we have to plant a solution. So the second step is as follows. We simply relabel the vertices of, say, the second graph, G prime, with a uniform permutation pi star. So this pi star is the planted solution. And now we observe G and H, which is the relabeled version of J prime, of G prime. All right, so if you look closely, it is easy to see that the marginals of G and H are simply Erdős-Rényi random graphs with average degree lambda. So the parameters of these models are n, the number of nodes, lambda, the mean degree of the graphs, and s, which is the correlation parameter, as you can see. So just to illustrate, well, we first draw a G and G prime, and then we blend a permutation, and we end up with two graphs, G and H. So you see that these graphs here are correlated. They have a decent amount of common edges, and there it's more difficult to see that they are correlated because we have this relabeling. So graph matching is simply recovering this relabeling. And this is the main goal, right? They estimate the latent vertex correspondence pi star. And here I want to emphasize on the fact that we are in a sparse regime where the average degree of the graphs is constant and the correlation also is constant. Okay, so these are quantities that are not scaling with n. And several remarks to start with. First, if we are looking at the maximum a posteriori estimator of pi star, it's easy to see that we end up with solving the quadratic assignment problem I was talking about before. So this is maybe the relation between the two problems, right? The quadratic assignment problem is the maximum a posteriori of the planted version. Another remark, interestingly, is that we cannot hope for exact recovery in this setting here. We only hope for partial recovery. So why it is impossible to match every node? Well, simply in the regime, it's not difficult to see that we will have a fraction of the nodes that will be isolated in G and in H. If I give you some nodes that are isolated in the first graph and some other nodes that are isolated in the second graph, well, there is no way to match them better than just random guess, right? So we know that just for this simple reason, we cannot hope for a fraction one of the nodes that will be correctly matched. So we need to define a measure of performance for our algorithm. And as I said, we cannot hope for exact recovery. So we are asking our estimator to perform well on some subset of the node set. So for any subset C here, we are looking at an estimator pi hat, which is 1-to-1 from C to 1n. And the overlap is defined as follows. We just look at the number of nodes that are correctly matched in C, okay, and we divide by n to get a fraction. So pi hat here only consists in a partial matching, all right? So if we think of pairs, we won't have n pairs necessarily in pi hat. We can only have, say, 50% of the nodes that are matched. But what we want is that the overlap is strictly positive and as high as possible. Conversely, the error fraction is simply the number of nodes that are not correctly matched on C by pi hat. Also here divided by n to get a fraction. So we now define two different notions. First of all, we say that a sequence of estimator achieves partial recovery if the overlap is strictly positive with high probability. All right, so this is very natural. We want, say, to be able to recover at least 30% of the nodes. Okay, so this is partial recovery. But when we think of applications, well, if I give you some pairs, say if I take C equals the whole node set, I give you then n pairs, and I say among these n pairs, only 30% of them are correct. Of course, your question will be where? Which are the pairs that I can really believe in, right? So this is a bit difficult if we just impose partial recovery. Partial recovery is not sufficient for what we really want. So we define one-sided partial recovery, which consists in partial recovery plus imposing that the error is vanishing with high probability. So we want to restrain the set C, But on that set C, we want an estimator that more or less is with high probability correct. Okay, so we want to output some matched pairs that are very likely to be correct, and no wrong matched pairs. Okay, so what we investigated in this paper is a local approach on this problem. Since we are on a sparse regime, we'll see that there is a connection between this graph alignment problem and another one, which is the correlation detection in trees. So why is that so? Well, now we are looking only at the marginal. Instead of, instead of maximizing a global objective here, we are looking at maximizing local objectives, which is simply finding for a given node I, we want to find its match vertex in the other graph. So if we look at two nodes, I and U, we simply ask the question, well, is U matched with I by the underlying vertex correspondence? Okay, so this question is very simple. And one possible answer to get a polynomial time algorithm that succeeds is to look at local neighborhoods in the two graphs. So if you look at the neighborhoods of I and U, so I in G and U in H, we will end up with trees in this setting. Okay, we have a constant mean degree. We know that this model is locally tree-like. So what we are looking at are two trees. And then the problem on graphs marginally becomes a problem on trees. Okay, and what we want to test actually is whether the two trees are somehow correlated or not. Okay, so this is an hypothesis testing problem on trees. And what are the two hypotheses? So if you look at the neighborhoods of I and U at some depth D, well, if U and I are actually matched, what we end up with are two correlated Galton-Watson trees of offspring Poisson of lambda. So the marginals are always Poisson of lambda, but in the case where U and I are matched, in this case, we'll end up with a substantial intersection tree, which is another Galton-Watson tree of parameter Poisson of lambda S. Okay, conversely, if U and I are not matched, as a first approximation, we can say that the two trees that we observe will be independent Galton-Watson trees with the same marginal distributions. So you see here that the two hypotheses are whether the trees are correlated or not. And we want to test the one model versus the null model. Null model being the model where the trees are simply independent. So for this kind of hypothesis tests, it is widely known that one optimal test is based on the likelihood ratio, so namely the ratio between the two probabilities of observing two trees T and T prime. Okay, and if we look at this likelihood ratio, what's quite interesting is that it enjoys actually a recursive computation, which writes as follows. So you see that the computation is quite involved, but namely this is because when you look at the likelihood ratio on two trees at depth D, we first have to distinguish the number of common vertices, which is K here. This term here is linked to the probability that the two roots have K common vertices, given that they have degree C and C prime. And then we are not sure about the relabelings, right? So we want to sum over all possible relabelings of the K common children in the first and in the second tree. Okay, and given these relabelings, we are computing a product of likelihood ratios for all pairs at depth D-1 this time. So you see, this recursive computation is quite natural, and it actually brings a nice polynomial time message passing algorithm in the graph. So if you want to compute every likelihood ratio at every pair of nodes. This will give you a score that will tell you whether the two nodes are likely to be matched or not. And this algorithm uses this recursive computation and is polynomial time in terms of the number of nodes n, when d is taken to be log n. So in the paper, we have a main result about this tree problem. And in this tree problem, we want to consider also one-sided tests. Okay, this is the analog to one-sided partial recovery. So the one-sided test is a test that will have a vanishing type 1 error, so namely no wrong matches, and a non-vanishing power. Of course, we want the test to be able to distinguish correlated trees with a positive probability. So the result, the main theorem is as follows. We look at the KL divergence between the two distributions, and we find some sufficient and necessary conditions for there to be a one-sided test, discriminating P0 and P1. The first one is to ensure that KLD, so the KL divergence goes to infinity when the depth goes to infinity, and that lambda s is greater than 1. And the other one is to observe that when there exists a one-sided test, we actually have that with positive probability under a model P1, this likelihood ratio will diverge at a very high rate. You see here a double exponential rate as a function of d. So this will lead us maybe to design our threshold in our algorithm, right? It says basically that we can take a super exponential threshold, and this will enable to detect a positive fraction of good matches and a vanishing fraction of wrong matches. Okay, so if you want more details on this theorem, please have a look at our paper in which we give some more involved conditions on the parameters for these conditions to hold or to fail. And another result is that actually makes the link between the two problems, right? So if we have a given range of parameters for which one-sided correlation detection is feasible in trees, and then this implies that one-sided partial alignment is feasible in the Erdos-Renyi model, and it is achieved in polynomial time by our message passing algorithm. Okay, so this is exactly showing that there's a strong connection between these two problems. So for many inference problems, what we like to do is to sum up the results in what is called a phase diagram, okay, showing several range of parameters for which the problem may be possible, impossible, easy, or difficult. So let's start with a previously known result. We previously know that under the condition lambda s less than 1, partial recovery is simply impossible, right? There is no algorithm that can succeed in outputting an estimator which will have a positive overlap. So this is a previous result, and another one, quite recent as well, by Wu, Xu, and Yu, shows that when lambda s is greater than 4, greater or equal than 4, then we can theoretically output an estimator that will achieve partial recovery with no computational constraints, however, right? So this estimator can be, for instance, the solution to the quadratic assignment problem, which is exponential time, but still will output a positive fraction of the nodes. In this paper, we studied the polynomial time feasibility of this problem. So first of all, we were able to show some sufficient conditions for the existence of one-sided tests in the tree problem based on the study of Kullback-Leibel divergence or the study of the number of automorphisms in a Galton-Watson tree. And this leads to the following green easy phase here, namely that in this phase, we were able to solve the problem in polynomial time. And you see that interestingly, this there is no frontier between the impossible and the easy phase. I mean, the frontier is sharp here when lambda is small. However, we also exhibited what we call a conjecture hard phase. So, namely, under the condition lambda s squared less or equal to 1, we were able to show that one-sided testability in the tree problem fails because the Kullback divergence is bounded. And in this regime, we can say that our algorithm fails. And we conjecture that the connection is actually runs deeper and that maybe no local algorithm will succeed for this task. So this is a first clue, according to us, maybe to exhibit what may be called a hard phase here. So we have this conjecture hard phase that interestingly intersects this feasibility regime here. Lambda s can be greater than 4, but lambda s squared can be less than 1 in the same time, right? And in this particular range here, well, we think this hard phase may be thicker, but still, in this regime here, we conjecture that the problem may not be feasible through local algorithms. All right, so as a conclusion, I have several take-home messages. So first, graph alignment is hard, as we saw in general, and we studied its blended version. More specifically, we studied a sparse regime where we established a link between the problem on graphs and a problem on trees, which is the correlation detection problem on trees that can be studied just per se independently. And this helped us derive a message passing algorithm that can reach good performances for our initial task. And that also seems to exhibit, as I said, a hard phase for this problem, right? As you saw, this phase diagram is still not totally clear. So one of the open questions may be, is there a sharp threshold for this algorithm to succeed? Can we be more precise on the exact regimes where this algorithm succeeds? And we believe that this can be easily extended. This approach can be easily extended to any tree-like graph models. All right, here I spoke about the Edger-Shreni model and the Galton-Watson trees that are linked, but in the general setting, in some preferential attachment models, we can hope for the exact same algorithm, except that we'll have maybe to change the distribution of the trees according to the distribution of the random graphs we're considering. However, there is a tree-like model for which graph alignment is very challenging, we believe, is the regular case, right? If you look at a regular random graph, of course you will have tree-like behavior, but all trees will look the same, right? They will look like deregular trees. So how can you detect correlation in these trees? Well, our algorithm here, of course, does not work. So another interesting question is, okay, can we study this graph alignment in the regular case? So here, of course, we believe that other methods may succeed, but no local method will be able to detect correlation in this case. Right, so thanks a lot for your attention, and please feel free to come and discuss and ask questions. Thanks a lot.